Hello everyone, Ken from Marine Mods here doing a little bench testing of our newest E38 high-speed GMLAN to J1939 and NEMA 2000 protocol. This ECM is connected to our programmable CAN-to-CAN gateway, which listens to the GM network traffic for specific gauge data. It then translates this data and rebroadcasts it onto another network, in this case a couple of marine displays running a NEMA protocol. To trick the ECM into believe it's actually running, we use a small Arduino board with a crank and cam simulator program. This simulator, along with a handful of potentiometers, feeds the ECM all the required sensor inputs to make it believe it's actually controlling a running engine. Along with this mess of wires and sensors, our ECM's CAN bus network is connected to a CAN-to-CAN gateway and a pair of common marine displays. It's also on a separate network a Bluetooth dongle supplying data to a tablet running the popular OBD2 Torque app. Powering up our ECM, we can see both of our marine displays immediately come to life, followed by the tablet on the left running the Torque app. Now let's tell our Arduino to generate a crank, pulse, and cam signal. And as you can see on all the displays, we have an RPM reading of about 1350 RPMs. One of the major advantages to our gateway translating the native GM protocol is the speed at which the RPM signal is replicated. As you can see on the right, it's very quick as compared to on the left. In OBD2, it has to request this RPM and then wait for it to come back, which gives it some lag. The default tables in our factory tune limits our scaling to about 8,000 RPMs maximum. I'd have to investigate further to see if this table can be modified to increase that number. Using a square wave pulse signal generator, I can also feed our ECM the correct input values on the vehicle speed sensor signal wire to make it think we're moving down the highway. I have the scaling set on this generator at about 11 miles per hour on each step. On the NEMA network side, we actually translate the speed signal into what's known as speed through the water to avoid conflicts with any other GPS unit that may be active on the network. As you might notice on the marine displays, our top speed was shown in excess of 204 miles an hour. In place of a transmission, I like these little Dakota Digital GPS and accelerometer based speed signal generators. When used along with a tuner tool, you can make speedo adjustments and give any ECM an extremely accurate vehicle speed signal. Certain tables in a tune can actually use this speed data for torque limiting and speed limiting factors. Next, let's have a look at our fuel level gauge. The E38 LS ECU can be set up with either a single or dual tank level input by default, which the ECM then totals into a single gauge value. This high-speed GMLAN value is padded so the factory gauge doesn't fluctuate on hills and such. Notice how the gauge on the Lowrance moves very slow compared to the OBD2 gauge on the left. Next up is our engine vacuum and boost gauge. Still working out some details on the vacuum side, but 5 psi is about what the ECM will output as a boost level by default. For readings higher than this, we require a different map sensor and some rescaling of the tables in the tune file. Now let's have a look at the engine load value. I like to have this available in marine applications. Like most other non-critical engine values, the NEMA protocol updates the load at 1 Hz or 1 time per second. This value is calculated off of RPM, MAF, throttle, and other input values. These calculations are used by other nodes on the GM network, like the TCM and traction control. In a marine environment, we can use this to see how hard the engine is actually working with certain prop setups or boat weight. Higher the load, harder the engine is working. Next gauge on our list is our IAT, or intake air temperature sensor. On forced induction applications, this is typically the temperature after the charge cooler. The NEMA 2000 protocol doesn't offer an IAT gauge option, so we have to assign an IAT to another value. Here I prefer to use the outside air temperature under the environmental parameters. This works well in a single engine application, but for tool engines there is other gauge inputs that we can use. Our next gauge on our temperature list is our engine coolant temperature, bottom right on the OBD2 display, and the big left gauge on the Lowrance. As you can see, temperature is padded slightly on the GMLAN protocol compared to our OBD2. Moving right along, let's have a look at engine oil pressure. Here again, GM pads the gauge, but not as much as some of the others. This factory ECU can display values up to 140 psi, which should cover just about any engine oil pump application. The last gauge I want to cover today is the EOT, or engine oil temperature. While all of the LS engine variants came from the factory with an oil temp sensor in the pan, even the Corvette used an estimated EOT value for ECM tables and displayed in the driver's information center. From what I've found, the calculated EOT value is based off of coolant temperature, IAT, engine oil pressure, and engine load, along with RPM. In a marine environment with sufficient cooling flow, oil temps should run considerably lower than those estimated by the factory ECM. With a slight modification to our factory OS, we can reassign pin 23 in the C2 connector to read a true EOT sensor input. Then our marine or J1939 displays will also receive the correct EOT values. Some other marine-friendly E38 OS mods currently in the works include water pressure sensor, fuel pressure sensor, and a wideband O2 data input. That concludes our demonstration, and I will leave you now with sights and sounds provided by one of our beta testers.